Understanding how objects move is one of the oldest applications of calculus, but it's still one of the most important. Using derivatives and integrals, we can describe and understand the motion of everything from massive planets to subatomic particles, and everything in between. We've now reached the halfway point in our lessons. Take a moment to celebrate that, by the way. Along the way, we've seen a number of different applications of derivatives and integrals. I've done my best to select a variety of examples that span many different fields: biology, physics, computer science, economics, and business, just to name a few, so that you can see just how widely useful the tools of calculus can be. But there's one particular application that's especially important: motion. I mean, there's a reason that the image I've been using for this course is a person riding a bicycle. We can use motion to demonstrate many of the concepts we've learned about so far in this course, and I think it's a great way to bring those concepts together. So here's our situation. Imagine a block attached to a spring lying on a frictionless table. Suppose we stretch out the spring from its equilibrium position, perhaps by 3 centimeters, and then let it go so that it oscillates back and forth, with its position described by some function, say 3 cosine of 5t, where t is measured in seconds. Now notice a few things to start off with. First of all, we're only considering motion in one dimension, back and forth along a straight line. And then also notice we're using x as the dependent variable. That's a little different. Most of the time in math, x is the independent variable and y is the dependent variable. But here, x depends on t. The horizontal position of the block depends on how much time has passed since we let it go. So that's why it's often so important to focus not on the symbols themselves, but rather the role they're playing in the problem. Okay, so what can calculus tell us about the motion of this spring? Well, the derivative of the position would tell us the rate at which the position is changing at any moment in time. So in other words, how fast it's going. We call that the velocity. Since x is measured in centimeters and t is measured in seconds, the velocity is measured in centimeters per second. And if we use the chain rule, then we have that the velocity at any given time t is equal to -15 times the sine of 5t. So for example, at t equals 1 second, the velocity of the spring is about 14.38 centimeters per second, while at t equals 1.5 seconds, the velocity is about -14.06 centimeters per second. That's right, velocity can be positive or negative, since it indicates both the speed and the direction. Here, a positive velocity means the block is moving to the right, and a negative velocity means the block is moving to the left. In that latter case, by the way, we'd say that the speed is positive 14.06 centimeters per second. In other words, speed is the absolute value of velocity. Okay, let's take another derivative. The derivative of velocity, which is the second derivative of position, will tell us the rate at which the velocity is changing at any given time. It's the rate of change of the rate of change. That's what we call acceleration. And once again, using the chain rule, we get that the acceleration is -75 times the cosine of 5t. Just like velocity, by the way, acceleration can be positive or negative. For example, at t equals 1, the acceleration is -21.27 centimeters per second, or we usually abbreviate that as centimeters per second squared. One interesting thing to notice, by the way, is that the block's acceleration is always equal to -25 times its position, which kind of makes sense if you think about the motion of the spring. When it's stretched out to the right, the spring tries to pull it to the left. And when it's compressed to the left, the spring tries to push it to the right. Since Newton's second law says that force, net force, is equal to mass times acceleration, that means you can often think of acceleration in terms of force. A positive acceleration means the net force is trying to push the object in the positive direction, and a negative acceleration means the net force is trying to push the object in the negative direction. Okay, so using the velocity and acceleration, there are a number of other questions that we could ask and answer. When's the object speeding up? When's it slowing down? What's its minimum speed? What's its maximum speed? And when does it reach those minimum and maximum speeds? We'll tackle these questions in class pretty soon, though you should start pondering them now. By the way, we could keep taking derivatives if we wanted to. For example, the third derivative of position is sometimes called jerk. And the fourth derivative and onward have some interesting names. Physicists have a special sense of humor, we'll say. But in practice, all you usually need for most applications is the first derivative of position, the velocity, and the second derivative, which is acceleration. That's enough to solve most real-world problems. All this talk about motion gives us a good opportunity to use our new tools we've developed to look at an old problem, dropping a ball and figuring out when it'll hit the ground. Remember, we did that in the very first video on dimensional analysis, and we used the dimensions of length and time to get pretty close to finding a formula for the right answer. But there was one part we couldn't do: finding the scale factor, that 2 under the square root. That's the kind of thing that you can only figure out through either collecting data or understanding the principles behind the problem. At this point though, with derivatives and integrals under our belts, we actually have the tools to do exactly that. In fact, we'll actually do something that mathematicians often do here: solve a more general problem and then apply it to our specific situation. Let's suppose that an object has constant acceleration a, which is a pretty reasonable assumption to make for a problem like this. So that means that the second derivative of position is equal to that number a. This is something called a differential equation, which means that we know something about the derivative or derivatives of a function, in this case the second derivative, and we want to try to figure out what the original function must be. We'll talk about differential equations a little later in the course, but for now, what we'll do is try to work our way back up to the position, which we traditionally label S. Seems like a bit of a weird choice for a letter, but it actually comes from the Latin word spatium, meaning space, like the position in space where our object is located. Okay, first of all, since acceleration is the derivative of velocity, velocity is an antiderivative of acceleration. The most general antiderivative of a, that is, the indefinite integral, is a times t plus some constant c. If we differentiate that, we will in fact get a. Next, since velocity is itself the derivative of position, then position is an antiderivative of velocity. So if we once again find the indefinite integral, we get 1/2 times a times t squared through the anti-power rule, plus c times t, plus another constant. Let's call it k. So the general solution of our differential equation is s equals 1/2 at squared plus ct plus k. But we can actually do more here. If we plug in t equals 0, then the velocity just comes out to c, and the position is just k. So that means that c is actually the initial velocity of the object, and k is the initial position. So we'll write those as v0 and s0, respectively. Pairing a differential equation with some initial conditions is what we usually call an initial value problem, and solving it lets us more precisely describe the particular solution of the equation that we're interested in. So the solution to our initial value problem tells us that the position of an object at any given time t is the initial position s0 plus the initial velocity v0 times t, the time elapsed, plus 1/2 times the acceleration times t squared. Now, if you've taken a physics class in high school, there's a good chance you've seen this equation, but perhaps you just had it given to you. Using calculus, we're able to see exactly where it comes from. And of course, you can check that if you take the derivative of this twice with respect to time, you do in fact get the constant acceleration a. Okay, that's the general situation. Let's think about dropping our ball. We'll write h for height instead of s for position, just to make it a little more familiar. And we'll also write negative g for our acceleration due to gravity. Negative because we're thinking of gravity as pointing downward toward the center of the Earth. So that's equal to either negative 32 feet per second squared or negative 9.8 meters per second squared. But writing it as negative g will give us something that works no matter what unit system we're in. Also, if we're just dropping the ball rather than throwing it up or down to begin with, then its initial velocity is 0. So that term just conveniently drops out of the equation. So now we have that the height, h of t, is equal to h0, our initial height, minus 1/2 times g times t squared. If we want to know when the ball hits the ground, then that's finding the value of t for which h of t is equal to 0. And if we solve for that value of t using a little algebra, then we end up getting twice the initial height divided by gravitational acceleration, all under a square root. That's the answer we got in the very first video. But it finally explains the 2 under the square root. It came from the factor of 1/2 in our original equation when we used the anti-power rule. At this point, we could plug in any height and make sure we have the right value of gravity based on what units we have, and we'll know exactly how long it'll take any object to reach the ground. Assuming lack of air resistance, of course, but that's a different story. So that's how calculus lets us describe motion. Differentiation takes you from position to velocity to acceleration, and integration takes us back from acceleration to velocity to position. Lots of other relationships in physics can be described using calculus as well. Force, momentum, energy, the list goes on and on. If you have indeed taken a physics class, you might want to go back to all those formulas you learned. I bet that now you can recognize the calculus that's been hiding in plain sight this entire time, waiting to get your attention and be discovered, like an apple falling on your head, or something like that.